we have Mark Waller. Mark was one of the original founders of Pulsic and served as vice president of R&D for 15 years. And now he's going to tell us about the new offering to the Pulsic tool suite, title being the essential requirements to close the growing analog productivity gap.
So hopefully you guys can see the screen there. So yes, I'm going to talk about closing the analog productivity gap. So let's think about digital first. When I'm talking about the gap, I'm talking about the gap between digital and analog. So 1985, how old was I then? 12. And the 386 came out, and that was an iconic chip at the time. 275,000 transistors. And then just last year, Apple bought out the M1. I think that's probably also an equally iconic chip. It has 16 billion transistors in it. So in 35 years, we've gone from 275,000 to 16 billion transistors. So it's actually 58,000 times more transistors in the M1 than there was in the 386. And really, it's not a 58,000 times increase in productivity. There are many other factors here. I'm sure Apple's team was bigger, but we could say that there's at least 1,000 time increase in design productivity from 1985 to 2020. And why is that? Well, a lot of that really comes down to the digital design flow. So the digital design flow here, I've really simplified it, but we start from RTL and behavioral synthesis, functional verification, and then netlist synthesis, place and route verification. There are other steps in there as well, obviously, but fundamentally that we have that flow, and that flow is really automated. I mean, every step pretty much of that flow is automated. The design engineers write code, either RTL or VHDL at the beginning, and then from that point onwards, really every step in that flow is automated, and it works really well. And we are, most of us in the software industry as well, and we're used to this idea where you have a upfront specification and you write some code, and then we have a compile-like tool chain that takes us to the output. And I know I'm oversimplifying, but fundamentally, that is the reason that we've had this huge increase in digital productivity in that time. That compile-like tool chain exists for digital design. It doesn't exist for analog design. There are bits of it. So simulation, optimization to a degree. There are lots of good optimization companies out there now that can help you do optimization, Monte Carlo simulations and such like. And then the verification flow is also very largely automated, but we really have this roadblock at the moment in the analog design flow. And that is this manual place and route step that is done. Now, it has improved. Over the last 20 years, there have been many improvements to that flow, but it's fundamentally still manual. So we've got parameterized cells, and people aren't drawing rubylith and like drawing every shape anymore. We have templated layout generators. Auto abutment really speeds things up. And overall, there's probably been a 10 times productivity improvement. Average layout engineer will sit down today and achieve 10 times as many transistors in layout in a day than they might have done that 35 years ago. But compare that to the 1,000 times productivity improvement that there's been in digital, and you can see that there's this massive gap. And it hasn't even kept up with the speed of processing. So whereas the increasing speed of microprocessors has accelerated the development of microprocessors, the increasing speed of microprocessors hasn't accelerated the speed of analog design. There have been many, many attempts to do this. Really, the EDA history is full of companies that have tried to automate analog layout, but they've never really succeeded. And one of the reasons for that is people have seen these really successful algorithms in the digital domain, and they've tried to apply those algorithms or modify those algorithms and apply them to the analog domain. They're typically computer science, graph-based, graph theory, types of algorithms, and they've tried to apply them to digital design. But by and large, they've given very poor quality of results, or not sufficiently good quality quality of some results, or they've taken a lot of setup, a lot of constraints, or those sorts of things in order to make them work. And we've got to this point now where I think many analog designers believe it's just too complicated. It can't be done. They've seen it tried so many times. They've seen really clever people try and do this, and it can't be done. And really, lots of people think it can't be solved. So these are key questions. And about 7 years ago, we sat down at Pulsic and we thought about these questions. We're being asked by our customers to look at this problem. We have a long history in custom design. We've been around for over 20 years doing custom design. And we were being asked, can we apply your technology to analog design? And at the time, our answer was, no, it doesn't work for analog design.
Good, I like it too.
So we sat down and we asked ourselves, and I think really we started to say, what attributes does analog layout need in order to be able to be successful? And we came up with these 6 essential requirements. So we basically thought there are 6 things. So these are not necessarily technology requirements. These are things that the tool must do. And this is what the rest of the presentation is about. So the first one, and I think this is really important, of our 6 things, is the tool must understand analog structures. It's not a wire length space optimization problem like it is in digital. It really has to understand these structures and understand how they work. So it needs to recognize the differential pairs, current mirror, cascodes, resistor ladders, band gap structures, all these common analog structures that exist in all of our chips. And it needs to recognize those structures. It then needs to generate constraints automatically. One of the biggest problems with previous generations of analog tools is that the tool has required the user to set things up. It's required the user to say, these things must match, that must be aligned vertically, this must be symmetry, that sort of thing. And it could take longer to set up the tool than it did to do the layout by hand. And so examples of that, it must create symmetrical layout constraints and common endpoint constraints, maximum dispersion where needed, match layout, dummy insertion, and many, many different more things. So it must be able to recognize the constraints for itself without needing someone to tell it. The third of our key requirements, we said it must understand analog layout strategies. Analog designers are real experts. There's a huge amount of learning and experience goes into analog design, and any tool must capture that experience and learning and try and use those features in the tool. Simple things, well, I say simple things, things that analog designers think about are current flow and signal flow through the circuit. They would think about simple things like reshaping resistor fingers and okay, can I get this down? Using power downs as dummies around devices. All these sorts of things really improve the quality of results, and any tool must take account of those things. The next thing on our 6 things, so this is the 4th thing, was a true understanding of DRC. So not just the ability to check. There are lots of DRC checking tools, but the ability to not create DRC errors in the first place, and that really at an analog level where you're dealing with these base layers, the diffusion and well shapes and active layers and poly is a really complicated problem. And actually even most manual designers will draw a layout and then they'll run the checker and then they'll fix the errors and working that sort of loop. That is not going to work for analog automation. So the tool has really got to understand the design rules at a much, much deeper level. The 5th thing is flexibility. So I talked about all those constraints. These constraints cannot be hard and fast rules. We have spent a long time now talking to analog designers all around the world, and they will say things like, I always use 2-row current mirrors, always, always, always. And so we would make a design that had 2-row current mirrors in, and then they'd say, actually, in that case, it doesn't work. Yeah, I probably would use a row current mirror there. So it's really easy to over constrain the problem, and the tool needs to have some intelligence built into it to know not just how to create those constraints, but how to flex those constraints and which ones to ignore, and the sort of priorities in what it's doing. And that's the sort of decision that designers are making all the time. They're making it subconsciously quite often, but in a tool, we've got to build that into how the tool works. The final thing, I've got the big easy button. I think analog flows are already very complicated. The circuit designer is already having to deal with schematic and a complex hierarchical schematic. They're having to deal with simulation tools and optimization tools. They're having to deal with LDE analysis and all the Monte Carlo analysis and all these things. And we've really got to make our role here to make the flow easier for those designers, not more difficult. So the big easy button, really you want a single click flow. You want it to be like that compiler to give you a good result. So there are 6 things. And like I said, we've been working for a few years now. And just earlier this year, we released the first version of our tool. And we call this Animate Preview. So I'm going to give you a very quick overview of Animate Preview. So Animate Preview works inside your existing open access schematic editor. So the idea of Animate Preview is you open your schematic, and as soon as you open your schematic, it actually has a look at that schematic, it opens it as well, and it starts creating a layout preview for you. And you can see the little window in the bottom left-hand corner here. Animate Preview runs automatically in the background without any interaction. I said a single click flow, it's actually a 0-click flow. It just does it, and it creates a layout preview for your circuit while you're editing your schematic. So you can keep on editing, that's fine. It'll create a layout preview for you, and it displays it down there in the bottom left-hand corner. So you can expand this preview here, and you can get an enlarged view of that preview. It's really analog aware. It is analyzing your circuit. It's recognizing the differential pairs and the current mirrors. It knows about wells and making them LVS correct and putting the devices in the correct wells and drawing the guard rings and matching and everything else. And in fact, in this design here, you can see the red and green are showing left-right symmetry in our op-amp type design here. And it's recognized, the picture is showing that we've highlighted one of the instances there in the differential pair, and it's placed those in a cross-quad pattern, typically a typical cross-quad pattern in the center of the design. And you can also get, at this level, an accurate area estimate for your circuit. So it can help you in your floor planning flow. Quite often, designers are waiting for analog information, like how big is this block going to be, what sort of shape and size it's going to be, because I've got to fit it in on the rest of my SoC. And it can help you get that information very quickly as well. So actually, I'm going to go back a slide here. The tool is actually using your PDK, your DRC rules. This is actual layout here. It's drawn slightly differently in this case, but it's really using the open access database and the P cells and the PDK and the DRC rules and making real layout in the background. You can zoom in, and this is the customization GUI. You can see here that it doesn't create just one layout. It actually creates multiple layouts for each circuit, and it displays them to you. So multiple variations. You can see how your circuit would look in different kind of aspect ratios and different placement topologies. It's recognized the constraints automatically. Like I said, it's recognized the differential pair and the cascade current mirror and some other current mirrors in that circuit, and it's highlighted the critical nets. There's zero human setup in this at all. It has just looked at that circuit and recognized it for itself. But you can edit those if you want to. So we try to have this kind of very light touch where you don't need to interact, but if you want to, you can. So for example, I could choose cross quad. In fact, that's the default, but I could choose cross quad or maximum dispersion for my differential pair. And then we have a version of the tool called Animate Preview Plus, and this will actually let you save the completed layout back to the open access database. The current version saves all the instances, the full connectivity, the well shapes and guard rings, etc. It also uses your P cells, like you can see there, and it puts in what we call base layer routing. So it'll get polyheads and contacts up to metal 1, and you can export that. Actually, the tool is doing a lot of routing, and there is a lot of routing in the design and increasingly more, but we're not exporting that yet in this version, but you can see we get up to that base layer of routing. So just a few features. It works inside Cadence Virtuoso schematic window, and it uses open access, your existing technology and your PDK. It creates these layout previews in seconds or maybe minutes, but it isn't hours. You haven't got to do any interaction at all. It updates automatically when you do check and save. It understands these analog structures, and then you have the customized window that you can use. And actually, Animate Preview is free. You can download it and use it in your design flow today. The Plus version, where you save the layout, is the version you have to pay for. And what are the advantages? Well, the advantages are it gives you very fast layout previews while you're identifying your circuit. You can identify those circuit issues before going layout. So have you got any mismatched devices? Have you got bad parameterizations? Did you just not realize how large this was going to be and how it's going to fit together? All those sorts of things. And you can include that layout information and process earlier in your design flow. And by doing that, you can reduce the design iterations. And if you use Animate Preview Plus, you can also vastly accelerate the layout by using this high quality initial layout with Animate Preview Plus. So we're not quite there yet. I started off talking about this compiler-like flow, this single-click flow. We're not quite there yet, but we're making big steps in that direction. And already our tool can really improve the productivity of your flow. And I'll take some questions, but if you want to learn more, you can go to our website and learn more from there. So thank you very much. Any questions, guys?
Just a quick question. So this would use like say skill-based P cells within it, and so your tool sits within Virtuoso if we're using Virtuoso.
It's embedded. Yeah, I mean, it's not running as part of the Virtuoso process. It has that little window. It's running in the background, but we display the results in that little. Perhaps I'll go back to it here. Into the little window in the corner in Virtuoso. Yeah. Right.
And that window on the left with the schematic, is that Virtuoso? It looks different.
It's not Virtuoso. No, I don't have permission from Cadence to show Virtuoso.
Ah. So. Okay. Thanks.
You're welcome. Any other questions?
If none, I have one.
Yeah,
sure. The case where it creates the multiple variants of the layout, does the user have any control over setting the criteria of how it would do that?
So what the user has control over is you can come in here and although the constraints are automatically generated, you can come and change them. And it always tries to produce a range of variants for you. So a range of aspect ratios. And it's always trying to make them as small as possible. There are other controls. In this case, for example, it's shown symmetrical layout there. We've got this left-right symmetry. You can say, actually, I don't care about symmetrical layout. Just try and make it as small as you can, and you can do that sort of thing. And you can do other things like setting pin sides. So you can say the input pins are on the left and the output pins are on the right, or whatever you like, or on the north or the south. So you can, yes, you can control the type of layout that it's producing and like pin direction, etc.
Wow.
I have another question.
Sure.
Looking at your slide that says Animate Preview Plus, where you're showing an example of layout with your P cells and poly heads with contacts up to M1 and so on. So I sent a screenshot of this to my layout guy. He's very concerned about that you've got different devices there, and I think we would want to put dummies around, around each of these groups of devices to improve matching. So can you tell your software to introduce surround the care about devices with matching devices and so on like that?
Absolutely, you can, and you have a lot of control over that. I didn't point this out on this picture here. The gray devices are dummies, so it's put dummies at the ends of the rows by default, but you can also tell it to always do it as a project file or on a case-by-case basis to put a ring of dummies around those sensitive substructures. So if you want a ring of dummies around the differential pair, it'll do that. And you can also, another way of doing that would be to put a guard ring around each of those structures, and you can do that as well.
Okay, thank you very much.
Yeah, you're welcome. Oh, thank you, guys.
Hearing no questions, thank you very much, Mark. Excellent presentation.
Thank you.